Today we're excited to have Aninda Sinha give us a talk about entanglement and scattering and the S-matrix theory. And we're especially thankful because it's pretty late for him in India, and he kindly agreed to give this talk this time of the night for him. All right, thanks so much. Please.
Thanks, Nima. Thank you very much for the invitation, and it's fine that these are strange times, so I am pretty sure that we have to work in different time frames. So I'm going to tell you about entanglement and scattering and the S-matrix bootstrap. And so basically it'll have to do with trying to find out or find our way in isolating an interesting question related to quantum information theoretic measures and relate them to scattering. So I will talk about entanglement and two-to-two scattering, and you can ask why would you want to study this. So for starters, you might want to distinguish density matrices in a scattering process. I will make this more precise, what this means by distinguishing density matrices. Or you may also want to ask if you have two different descriptions, maybe two different competing theories, and you want to ask which theory describes your scattering better. And you want to do this quantitatively. And you will see that some of these ideas will come in handy. Another reason, and this is one of the main reasons why at least I got interested in this problem, was because of the fact that there was this recent attempt to reincarnate the S-matrix bootstrap. And I will briefly review the philosophy of the S-matrix bootstrap. So basically, the bootstrap gives us a space of S-matrices because it gives you a bunch of allowed theories. And of course, in order to constrain your theory space further, you have to put in more and more constraints. But essentially, with the minimum number of constraints, you'll get a space of allowed S-matrices. And you want to ask, for instance, how would you say how close to S-matrices are? So in this figure, for instance, I will explain this figure as the talk progresses, but this describes pion scattering. There are three kinds of pions, and this figure describes a particular process. The y-axis is a special kind of parameter, which is called an Adler zero. I will tell you what the Adler zero is, and the x-axis is another kind of Adler zero. I will describe them in detail as the talk progresses. And somewhere in this blue region, which is the allowed region, the river is, we call it a river because it looks like a river, and these are the banks of the river. So anything within the river is an allowed theory. I will explain more in detail what an allowed theory means, what makes it allowed and what makes it disallowed. But this red cross that is sitting here is basically what comes from what is called chiral perturbation theory. And the standard model actually sits very close to this region. And so you might want to ask that, okay, so suppose I took a random S-matrix somewhere else on the river, then how close is that S-matrix to the red cross? That could be one question that you would be interested in. Even more ambitiously, you might want to ask, is there a quantum information motivated selection principle in the space of S-matrices that says that the standard model is special? You want such a selection principle because once you have a non-perturbative set of constraints that constrains your space of S-matrices, then you would require a creative way to say that this is the S-matrix that describes nature. But basically, this is a very fertile play area because I think trying to understand the S-matrix bootstrap in this language is very, very at a very preliminary stage, and there's a lot to be done. So just to sort of set the tone, let us briefly recall something about the conformal field theory bootstrap numerics so that we have something to sort of compare with and draw analogies with. So this is a popular plot that you will see in numerical bootstrap. So what this is, on the y-axis, you have the scaling dimension of the leading scalar operator that appears in the operator product expansion of two scalars. So for instance, suppose you are considering the three-dimensional Ising model, then, or even more familiar, if you consider the two-dimensional Ising model, then you have the spin field, and then in the OP of the spin field, you have the epsilon operator. So on the y-axis, you'll see the scaling dimension of the epsilon operator. And the x-axis is the scaling dimension of the fundamental scalar. And the Bootstrap tells you what is space of allowed theories. So for instance, suppose you're looking at the Ising model, which is basically the simplest version of this theory. This is the n scalar version, ON. So the Ising is for n equal to 1. And so anything below this line is an allowed theory, at least in the simplest setup where you're considering the scalar, the 4-point function of 4 identical phi fields. And then you can start generalizing it. You can consider O2, which is going to describe the universality class of superfluid helium, for instance, O3, which is the Heisenberg ferromagnet, and so on. And you will see that anything below this line is allowed, but the Ising model essentially lies at a kink, at a sharp bend. And same story happens for the O2, O3, and so on. So there is always a change in behavior. There's some knee or a kink or whatever you want to call it. But basically, that is one of the features that the interesting theories seem to lie in some special place in the space of theories.
Sorry, quick question.
Yes,
so,
yes.
So I guess this is a few years old, and I was just wondering, in the simplest example, say Ising, is there now some sort of simple physical understanding of what is going wrong if something is above that line, for example? Or it's just like completely some numerical result that has no interpretation and known interpretation?
Of course, I mean, you are trying to constrain the theories by demanding that the theories are unitary. So one of the things that you demand are the OP coefficients are real. So so that is one of the inputs. I think what goes wrong is that you lose unitarity when you go above this line. So for one. And of course, you get this by demanding crossing symmetry. But so far as I guess what you want to ask is that why is there a kink and why is there a sharp change in behavior here? So I mean, the kind of things that people say is that there are operators that decouple at this point. So it's roughly speaking, suppose you are considering the 5⁴ theory in quantum field theory, and then you're taking, you go to the fixed point. So you have the equations of motion, which will roughly look like del square phi is proportional to phi cubed. And phi cubed would be a primary operator in the original theory, but because of this relation, because of the equations of motion, it becomes a descendant state. And so it decouples from the set of primary operators. So that is the change in behavior. But to be honest, the kind of deep understanding that is that would satisfy us is still missing. So for instance, we don't know how to write down an equation for this kink, even in principle.
I see, thank you.
Okay, but the bottom line is that we won't require too many details of this plot, except the fact that there's something special that happens near some kink type feature. So what is the S-matrix bootstrap so far? So one can make a similar plot. So instead of having these scaling dimensions that are there on the y-axis and the x-axis, the way that the S-matrix bootstrap has been set up as of now, it can be set up differently, of course, but then as of now, what we have done or what people have considered is that on the y-axis, we have this special kind of Adler zero. S2 is basically this 2 is for the isospin, and this 0 is for also labels a kind of isospin. And you ask in this space, what are the allowed theories? And what constrains these theories is basically unitarity. So what are the theories that are constrained by unitarity? And then there are some mild inputs. So of course, in order to constrain the theory space more, you require to put in more inputs. And depending on what input you give, the theory space can be constrained even more. So the kind of thing that people have found are, for instance, some exclusion regions, which they call the lake. And there is also an inclusion region, which is called the peninsula, which is marked in P. I will go over all this later on. But basically, you'll get some interesting regions, interesting shape, and then somehow remarkably, the known experimental values which describes the standard model is close to the boundary of these allowed regions, regardless of how you sort of set up the problem. So, so one of the challenges is to understand why, or what is so special about what is happening here.
Sorry, another question. Is this, how many dimensions is this in?
Oh, this is real 3+1 dimensions. This is 2-to-2 scattering in describing pions scattering in four dimensions.
So does the story simplify significantly if you go to lower dimensions?
Yeah, I think so. And this is something that your colleague will be able to answer even more. So in 2 dimensions, of course, you can get some sort of match with analytic stuff as well. So what basically happens is that because you lose essentially one of the Mandelstam variables, your problem is no longer a problem in the space of S and T. So S and T are the Mandelstam variables, but it becomes a one-dimensional problem, one variable problem rather. So that's why it becomes significantly simpler. But of course, if you want to do real stuff, you have to be in 3+1 dimensions, or maybe in 2+1 dimensions. Yeah.
Sure, thank you.
Yeah. Okay. So I will describe some of these results and some of these interesting results for the S-matrix Bootstrap, and essentially tell you a little bit about our hunt for a selection principle. So what is so special about the standard model? So just to get you more interested in this question, so there are a couple of things that we'll focus on. One of them is a minimization of the total scattering cross-section, and I'll tell you why this is sort of the natural thing to do so far as the standard model is concerned. And then also another thing that we'll focus on is the minimization of a quantity called entanglement power. So just to whet your appetite, let me just describe the result a little bit so that you get familiar with some of what you're going to see. So as I told you that we will get a river of allowed S matrices. So the blue region is a river, and there are banks of the river. So this gray area is the upper bank, and this lower area C and D lie on the lower bank. And basically, just from unitarity, any of these theories which are lying on the riverbank or inside the river would be an allowed theory. I will tell you what constraints go in to get this river, but essentially it's unitarity and some mild inputs like positivity of certain scattering lengths, which I will tell you as the talk progresses. There are some interesting features here. So one feature is the straight line that I've drawn. So the straight line is the line which describes what are called the Lovelace-Shapiro model. So depending on how old you are, the Lovelace-Shapiro model was the precursor to modern string theory. So so it's basically this line would describe a version of the Lovelace-Shapiro models. And I'll tell you what this means. And the interesting thing is that the line of Lovelace-Shapiro model intersects the space of allowed S matrices at very interesting places. So obviously, 2 of the interesting places are A and B, and A is very close to the where the real standard model lives. So the standard model actually lives very close to region A. In the sense that the S matrices that live near region A match up with experiments, give you the correct scattering lengths, they have the correct Regge behavior, the correct spectrum, and so on. Now, there is another interesting line, which is this black line, which passes kind of through the middle of the river, but then it sort of kind of just touches A. This black line is a line of models where the total scattering cross-section is minimized. And And so just bear in mind that there are these interesting lines. There's this Lovelace-Shapiro line, and then there is this line of models where the total scattering cross-section is minimized. And somehow the Lovelace-Shapiro model and this line of total scattering cross-section being minimized intersect very close to the region where the standard model actually lives. Now I should tell you that making these plots or getting anything out interesting out of this numerically is a very time-consuming process. And in fact, this black line, which is, in my opinion, one of the most interesting results that we have found, is not there in version 1 of the paper. It took us quite a while to get this line, and it will appear in version 2 of the paper, which should be uploaded maybe in a couple of weeks' time. Anyhow, and what happens is that if you can plot entanglement power, again as a function of S naught, and superpose this on the space of allowed S matrices. And somehow, very interestingly, there appears to be a kind of a local minima, or maybe this is even a global minima. It requires a bit of more numerical work to determine whether this is a global or a local minima. And this entanglement power appears to be minimized precisely at the location of what I would call the standard model. So these are very interesting things, and the challenge is to try and understand them in the future. So this is based on a couple of papers that appeared last year. So the first paper was with Anjishnu Bose, who was an undergraduate student in IISc. He was doing his undergraduate thesis with me. Parthiv Halda, who was my graduate student. And he's going to finish next year, which means that he's going to apply for a postdoc position at the end of this year. Pritish Sinha, who was my master's student, and Shashwat Tiwari, who was again an undergraduate student. And then there was a follow-up work with Anjishnu and Shashwat. Okay, so let's begin by setting up some background. So let's talk about entanglement and 2-to-2 scattering. So 2-to-2 scattering, of course, the simplest case is when you have maybe scalar particles. You don't have to talk about other quantum numbers, but if you have other quantum numbers like spin, it will make things more interesting. But for the purpose of this talk, I will talk about 2-to-2 scattering of scalars. And it is not a toy problem, because pions, the chiral perturbation theory, in chiral perturbation theory, pions are scalars which transform in some global symmetry with some global, in the O3 model to be specific. And here, this is the sort of quintessential way that scattering is described in any textbook. You go to the center of mass frame, and A and B are the incoming particles, C and D are outgoing particles. And then at various angles, you place detectors, and basically the detectors collect whatever particles reach there. So just to simplify, but not simplify completely, but just to sort of get going, the initial state would be denoted by A, B. So A and B would be the collective sort of indices for the momenta of the A particle, maybe other quantum numbers that the A particle can carry, and similarly for B. And also for the final state, which would be C and D after scattering, would be labeled similarly. Now, because we are sort of imagining that there is a detector that is sitting at a specific angle, we are going to restrict the momenta of the final state by putting in some projection operator, which will sort of mimic the fact that there's a detector at angle theta. So S here is the S matrix, or the S matrix operator that takes you from the initial state to the final state. Now, after that, you have a density matrix for the final state particles, which is given by this. And then you decide to trace out the C particle. You could decide to trace out the D particle, doesn't make any difference. But you decide to trace out the C particle in this manner. So when we write something like this, of course, in momentum space, if it is a scalar particle, what is labeling C is just the momenta, and you are going to basically sum over the final state momenta of the C particle. So this is momentum space tracing, which is kind of not the usual way that you do entanglement entropy, because entanglement entropy, the way that you do it, at least in maybe when you think in terms of holography or in quantum mechanics, is either you trace over the quantum numbers like spin, or you trace over, or you consider position space tracing. But this is kind of different. This is the momentum space tracing. And just to sort of remind you that S and T are the usual Mandelstam invariants. Out of these, you can construct this cosine of the theta. So here, the costs of the angle, cosine of the angle that A and D make is given in terms of the Mandelstam invariants. So are there any questions regarding this setup? Okay, so let's continue. So after some lengthy algebra, it's straightforward, but it's still lengthy. What you will find for entanglement entropy, so you would calculate the usual von Neumann entropy by doing some straightforward but sort of complicated momentum space integrals. Using the replica trick, you would find that the entanglement entropy is given by log of V divided by T. So this is a spatial volume, and T is the time interval over which this process is happening. So this is not well defined. And then there would be some integral which would look kind of familiar, because in quantum mechanics, you would get an integral which looks like summation over probability times log of probability. So this is something that looks very similar to that, except that this curly P is not a probability distribution, in the sense that at each value of X, curly P is not necessarily less than 1, but it is a probability density in the sense that if you integrate, it is equal to 1. The formula makes it very clear that it is equal to 1. So what M here is the usual way that you write down the matrix element. So usually you write the S matrix as S equal to 1 plus I times T, and the T or M, whatever you want to call it, 1 plus I times M. And G here is sort of a support function, because I told you that there's a detector that is sitting at a particular angle. So G actually tells you that there's, it comes from the projection operator that we put in to sort of mimic the fact that there's a detector at an angle theta. And except for the fact that we put in a kind of a realistic sort of support for where the detector lives, the original momentum space tracing was considered by these people before our work. Sorry,
a quick question. Yeah. Oh yes. Yeah, you were just gonna go. I was just gonna ask a question about the divergence. Yes. Go ahead. Sorry.
Yes. Yeah. So this log piece is of course divergent, and then you would try to make maybe figure out a way to regularize this divergent, or maybe ask, can we consider a quantity where you can get rid of this divergent? But is that what you were asking, or you were asking something more?
Yeah. I was actually wondering about, so the K is dimensionful here?
Yes.
What is it exactly?
So this is the center of mass momentum. So this is like S. So the center of mass, center of mass energy. Yeah.
I see. It's just, I see. And then this is sort of, so this is an infrared divergence, right?
Yeah. So large volume would be an infrared divergent, whereas K square, yeah.
It's perfectly expected. Yeah, sure. Thanks.
Yeah. Okay. So just to remind you, so there's a divergent piece, and then there's this matrix element square, like what you would expect. And G is the support at angle X. Now, a quantity which, of course, is much studied, which is of a lot of use for various reasons, is called relative entropy, and relative entropy is defined in this way. You have two density matrices, and these two density matrices there are two different ways of thinking about these two density matrices. The way that this picture sort of tells you is that you could maybe consider a density matrix at angle theta 1, which corresponds to so whenever I say x is like cos theta. So x equal to x1 means it's cos of theta 1. And you could have another angle. So you have two different density matrices, and you could consider the relative entropy between these two density matrices. Of course, that is one way, but there is another way, which is basically you consider sitting at the same angle, but you have two different theories. And so basically you have two different M's, two different matrix elements that you'll get from your different theories.
Sorry, there's something I don't quite understand here. So
yes.
This is, so you do partial trace in momentum, and further, are you doing some sort of a partial trace on this S2 to come down to a particular angle?
No, so what we are doing is we're restricting the final state momenta. So after you restrict, because of the fact that cos theta is related to T and S in this way, you still get you don't get a particular value of T and S. So you get a spread of values in T and S. So it still becomes a function of S ultimately. So the final answer is still going to be a function of S.
Yes, but when you say density, can you go to your slide again? You say the density matrix at a particular theta. Maybe we could say, so rho 1 is a density matrix for what exactly?
So rho 1 is a density matrix that you would get by doing this calculation here, where the support function is kind of a Gaussian at that particular angle.
I see. Your projection operator is that what defines 1 and 2. Thanks so much.
Yes. Okay. Now, another importance of this relative entropy is that it gives you a way to distinguish between two density matrices. And so, for instance, suppose you have two different theories, and you're trying to understand whether you'll be able to say from the scattering, by studying the scattering problem, that which of your theories is preferred. So, in order to distinguish two theories, you require to essentially sort of have a large number of measurements, and the large number of measurements is governed by the relative entropy. So this relative entropy tells you how easy it is to distinguish between two different theories or two different density matrices. So if you have a large relative entropy, you would require a smaller number of measurements to distinguish. So of course, this is a familiar concept, but if somebody is interested in learning about them, so there's a very famous review by Vedral from 2001 and a very nice review by Ed Wheaton in 2018. So again, let's quickly go through some math. Essentially, another advantage of relative entropy is that these log v divided by t, this guy has cancelled out, and you are left with only some nice integral over these probability densities. It looks like a nice formula, and in fact, you have a probability density corresponding to a support function at theta 1, and you have another probability density with, corresponding to a support function at theta 2. And it's not very difficult to actually show that this relative entropy is positive. It just follows from properties of the fact that P, this curly P is a density. So let me just tell you how to do this calculation if you're considering two density matrices corresponding to the two different angles. So the way that you would do it is that your support function, this G that I was telling you about, is sort of a Gaussian support function. You can consider other support functions. We took Gaussian for convenience. So sigma is like the detector width. So how accurate your detector is. And then you can go ahead and do this calculation. You will find that there is a piece that depends, the leading piece depends on the detector width. So, it will look sort of what I would like to call classical. I like to call this piece classical because this is what you would get if you considered hard sphere scattering. This does not depend on the matrix element. And then you can calculate subleading terms in the expansion. So delta x here is basically the difference between the two angles. and you can expand by in small separation, small angular separation. The first subleading term, which I want to call dq, is an interesting object because it does not depend on sigma. So the sigma dependence is there in the hard sphere part. This guy does not depend on sigma, so it's basically in some sense independent of the detector resolution, and then you would get subleading terms. This dq part, which I would like to call as a universal part, has some interesting properties. First of all, it depends on the second derivative of the log of the ratios of the matrix element square. This second derivative is kind of important. It will come and play a role in a bit. Just keep in mind that there is a universal piece that depends on the second derivative. And then you can go ahead and study a bunch of standard theories. You can consider 5 to the 4th theory. It's fun to, once you have a bunch of theories, and you know the matrix elements, you can go ahead and plot these and figure out what they look like. So if 5 to the 4 at one loop would look, this universal piece dq takes on quite a simple form. It is proportional to lambda, and it sort of blows up in the forward limit. So the forward limit is basically when the emergent final state particles make 0 angle, or maybe 180-degree angle with the incoming particles. So you get 2 sharp peaks in the forward and the backward limits. You can consider this for string theory as well, because you know the 2-to-2 scattering for, say, the dilaton, the 4 dilaton scattering amplitudes in superstring theory. You can take sort of a low energy limit of that, and you will see that it has, again, a nice form. You can do this analytically, you can do it numerically, whatever you want. This is in some low energy limit where essentially you have not excited the higher string modes. If you excited the higher string modes, you will see this oscillating very vigorously. And that kind of makes sense because oscillations in relative entropy essentially means that you're losing distinguishability. But in the low energy limit, which is essentially the supergravity limit, you again get a nice form which you can determine analytically. Again, you have peaks in the forward and the backward limits. You can do it for an effective field theory. So chiral perturbation theory, which describes pion scattering, is a well-known effective field theory. And why is this kind of an important thing? Because effective field theory, of course, are not valid beyond a certain energy scale. And you can see that, okay, so for low enough energies, you do get this peak at the forward and the backward limit, but then beyond a certain thing, it turns over. So this is a feature that this is an effective field theory, not a fundamental theory. You can develop this a little bit more. You can actually get some more mileage out of these kind of considerations. So one thing that I wanted to describe to you are how to think about high energy limits of this relative entropy. So for that, I need to tell you a little bit about what is known about the high energy limits of these matrix elements for 2-to-2 scattering pertaining to pions. So this is something that people have analyzed a lot since the late 1950s. For this, you don't require to have appeal to perturbative quantum field theory. You can do this using certain techniques. Basically, it relies on partial wave expansions, certain mild assumptions about the locality of the theory, and again, certain mild assumptions about the high energy properties of the theory. So, but nothing about the details of the theory. You don't require a specific model where you do these calculations. So under general arguments, one can give general arguments that the matrix element square is bounded in the high energy limit. So this is for fixed angles. So x is fixed. X means cos of theta, so theta is fixed. But high energy means the Mandelstam invariant is much bigger than 4m square. M is the mass of the external state particle. you can actually, or people have showed that this takes on this sort of general form. Now, this exact dependence is not important for us. What is important is the kind of 1 minus x square factor raised to some positive p in the denominator. And this is kind of important because in the specific examples that we studied, I showed you that you have this kind of a peak in the forward and backward limit. And these general arguments also suggest the same kind of peaks. Using this form, you can actually show that the dq, which is what I was calling the universal part of relative entropy, is also bounded. It's bounded by this kind of a behavior. And just if you stare at it, you will find that 5, 3, 4, low energy string theory all respect this form. They respect this bound. Now,
I can ask a naive question. Maybe I should have asked this a little bit earlier. So you showed this really beautiful equation, which was the relative entropy expanded to second order in delta x squared. Yeah, exactly this one. So I'm just, it's somewhat tempting to try to integrate this equation and write down some information theoretic quantity equals some scattering amplitude thing. So yeah, have you guys tried something like this?
No, that's a great question. No, we have not tried that. Yeah. No, that's a great question.
We were looking for something. Okay. That's all. It's a very, oh, by the way, so x1 here is x1 plus x2 over, is it one of them or is it in the middle?
No, so because of the fact that, you could actually average it, but then because we were Taylor expanding, so x1 minus x2 goes to 0. So so in that limit, it doesn't make any difference.
I see. Yeah, it's just the second derivative. That's right. Thanks so much.
A consequence of this, of the fact that there is this high energy bounds, it's a simple consequence, but let me just spell it out, is that if you have a bound of this kind, it basically tells you that in the high energy limit, you have to work harder to distinguish between two density matrices in this way of thinking about things. Another sort of a corollary of doing all this hard work is that you can prove a very interesting property of Regge trajectories. Now, what are Regge trajectories? Of course, if you know a little bit about the history of string theory, this is one of the most important inputs how string theory originated. So let me just tell you a little bit about the phenomenology of pions. So there are 3 kinds of pions, pi 0, pi plus, and pi minus. And you can go to the particle data group handbook, and then you can write down the S variable, which describes the real part, which corresponds to the mass square, and the imaginary part, which corresponds to the decay rate of the pions. And you will find that the pions have, of course, I'm normalizing with respect to the mass of the real part of the mass of the pion, will have an imaginary part, which is quite many orders of magnitude smaller than the real part. So in some sense, if you think about what is happening on the complex plane, the pion mass is very close to the real axis. And then in these scattering processes, you start seeing resonances. Now, the resonances have various spins, J0, 1, 2, 3, 4, 5, 6. Now, not experimentally, you can't go, not much is known beyond spin 6. I think spin 6 is as much as what is known. And each of these resonances have some name. And the resonance is one of the peculiar properties is that the real part and the imaginary part are kind of competing. I mean, at least for this particular meson F0, which is called the sigma meson, the real part is as big as the imaginary part. The curious property is that if you plot the spin versus m squared, then what you generate is what is called the Chew-Frotchi plot, and you get a straight line. And of course, the challenge in the 1960s was to come up with a model which respected crossing symmetry and also gave this Regge behavior. And that, of course, is what was solved by the Veneziano model. Of course, phenomenologically, the Veneziano model did not agree with experiments because it gave the wrong slope. It later on was reinterpreted as a theory of gravity and so on that you now know. But phenomenologically, this is what you find. Now, of course, it's almost a straight line. It's not literally a straight line. And there are claims, sort of, again, these are semi-established, I would say, phenomenologically, that it's not really a straight line. It has some curvature. So this alpha 2 t square tells you how curved the trajectory is. If this curvature was 0, then you literally have a straight line, but it has some curvature. And the point is that suppose you use this formula inside the formula for the relative entropy, you would find that dq takes on this form, which so essentially it means that dq is directly proportional to this alpha 2. And it takes a bit of thought that look, in the high energy limits, we know that in the large energy regime, dq actually is a positive number, which essentially means that this alpha 2 should also be positive. And this is quite nice because, in fact, experiments seem to suggest that the curvature, this alpha 2, should be positive. So this dq is sensitive to this nonlinearity of trajectories, and in fact, you can sort of indirectly argue that this curvature of this trajectories has to be positive. Okay, and this is what I told you, that you compare with the high energy bounds, and you will find that alpha 2 is bigger than 0. So let me switch gear and tell you a little bit about bootstrapping quantum field theories, because I wanted to sort of connect up these quantum information theoretic ideas with the S-matrix bootstrap.
Sorry, one question about what we were just saying. So are you gonna argue why alpha 2 is positive from information theory or not? Are you? Oh
yeah, no. So I don't have an independent argument from information theory why this is true. Yeah, that's a great question. In fact, I mean, it's sort of, you would have thought that there's something like the positivity of relative entropy, but the point is that this is a subleading term. The leading term is already a sort of very, very positive, because sigma, we are working in the limit that sigma goes to 0. So it's a subleading term, and I don't know why a subleading term in relative entropy should be positive, but it's a great question.
I see. Thank you.
Yeah,
Thank you.
Okay. So let me quickly tell you a little bit about the history of the bootstrap. Now, so historically, you know that quantum field theory had a lot of problems initially, and it was a theory that was taken forward by the younger generation, because the founding fathers had sort of at various instances given up hope on quantum field theory. So Dirac actually abhorred quantum field theory. He was the sort of creator of relativistic quantum mechanics, but he famously actually sort of disowned quantum field theory. And there was this period where people like John Wheeler, Heisenberg, many others, they tried to think of other ways of thinking about quantum field theory. So Wheeler introduced the concept of the S-matrix, and in the middle of the war, where Heisenberg was supposedly building the bomb, he wrote some influential papers which sort of clarified some of the philosophical ideas behind what later on in the 1960s came to be known as the S-matrix bootstrap program. And specifically, it is called Choose Bootstrap because he was one of the proponents of the S-matrix bootstrap in the 1960s. So recently, after the success of the conformal bootstrap, people listed here started looking again at the problem of the S-matrix bootstrap. And I can safely tell you that it is a field that is very wide open. It is not as developed as the conformal bootstrap. There's a lot to be done here. So in fact, Martin Kruczynski in Purdue is also working in this. And it's safe to say that there are a lot of ideas, there are a lot of promising ideas here, a lot of things to explore. So this is sort of a quick historical summary. The idea of the S-matrix was introduced by Wheeler in 1937 and was taken forward by a lot of people, a lot of famous people, Landau, Chu, Mandelstam, Lehman, Martha, and so on. And the thing is that you use very basic principles, and the basic principles are things like Lorentz invariance, unitarity, analyticity. You don't have a perturbative expansion. You don't think in terms of a Lagrangian. You don't have to think in terms of perturbative quantum field theory, loops, and so on. And the question is, you have crossing conditions and unitarity, and the question is, are they constraining enough? And a favorite problem that people like to come back again and again is basically a favorite toy problem because it's sort of experimentally relevant. It's not just a toy problem. It's experimentally relevant. You can go and compare with experimental data, is the problem of pion scattering. So again, just to sort of tell you that you really can't make pions like you can make protons and scatter them. Pions are produced indirectly. They have small lifetime, although they are very close to the real axis. Still, in terms of seconds, the lifetime is really tiny. But nonetheless, you can still study this process indirectly and extract experimental quantities like, say, scattering lengths. You can also extract the spectrum of resonances and so on. But the reason why people want to study this process is because so far as a problem in complex analysis is concerned, it has a simpler analytic structure in the complex S-plane. So you can measure scattering lengths and effective ranges. Well, effective ranges, one does not have precise measurements, but scattering lengths you can measure. So A's here in this table are scattering lengths, and the B's are effective ranges. Now, I will give you a formula for what these scattering lengths and effective ranges mean. But essentially, the superscript here will correspond to isospin. So this is basically a problem having O3 symmetry, you can think of it. And there are three kinds of pions. So you can see the superscript running from 0, 1, and 2. And the subscript corresponds to the Lorentz spin. So that is what this table means. And you have results from chiral perturbation theory. So this first column is results from chiral perturbation theory, putting in various assumptions, because chiral perturbation theory is an effective field theory, which essentially means that in order to extract any numbers out of it, you will have to put in experimental input. And the last column here is an experimental column. So there are some experimental results that are known. And another thing that is known experimentally is a spectrum of resonances, which I told you. So just to sort of make you familiar with a bit more terminology that I'm going to use, you have an amplitude M. It is a function of two Mandelstam invariants because it's a 2-to-2 scattering. 2-to-2 scatterings are functions of two Mandelstam invariants. You can do a partial wave expansion in terms of Legendre polynomials. So you're in 4 dimensions. That's why you see Legendre polynomials. If you were in arbitrary dimensions, you would see Gegenmayer polynomials. And these FLs are the partial wave amplitudes, and which are constrained by unitarity. So this is the constraint. So just make mental note that one of the constraints is nonlinear. So you have FL square less than 1, whereas this one is linear. The imaginary part of FL is less than 1. And of course, it's an old problem. This is a sort of a very famous old book, which talks about the analytic structure in the complex S-plane to think about these amplitudes. Because basically, if you can analytically continue, you can describe different processes using the same analytic function. So basically, you'll have crossing symmetry to describe various processes. So a simple consequence of crossing symmetry, if you have, say, just scalars, say, imagine that you just had scalars without any isospin, then the problem that you would be trying to solve, the crossing symmetric problem, can be written in this language. M of st should be equal to M of ts. And you can try to do a partial wave expansion of both sides. And then, of course, as you know, if you have read the first chapter of Wien-Charles-Wheaton, that if there is pole in one channel, then in order to reproduce that pole in the cross channel, you require to sum over an infinite number of partial waves. And that's a notoriously hard problem. I mean, that is not the way to set it up. what you can do is actually work in a different set of variables. So this is sort of makes this somewhat more suited, because this particular variable has manifests the cut structure on the complex S plane. This is like a conformal transformation from the original variable. And in terms of these variables, you can expand the amplitude. So basically, you have parameterized your ignorance, or you have pushed your ignorance into the coefficients of this basis. This alpha ABC are the coefficients in the basis expansion, and our job is to use unitarity and what have you to constrain these alpha ABCs. So you can put in the FL square less than equal to 1 constraint. Remarkably, it turns out that this constraint can be recast into a semi-definite programming problem. And semi-definite programming is something that numerical conformal bootstrap people have developed a lot. And so, of course, once you have a technology that is ready, you might want to reuse it. It's a perfect problem to sort of export the already existing technology and study. So you want to constrain these parameters alpha ABCs using unitarity, and the pion scattering problem is a bit more generalization, a bit more generalized version of whatever I just now described. It has some global group theoretic indices, which basically are the isospins. So there are 3 kinds of isospins. So instead of just getting a partial wave expansion labeled by Lorentz spin, you also have to label it by isospin. That's all that is different. And just to sort of tell you what Adler zeros are, Weinberg showed long time back that to lowest order in chiral perturbation theory, these particular partial wave amplitudes, so this corresponds to the isospin 0, Lorentz spin 0, and this particular amplitude corresponds to the isospin 2, Lorentz spin 0, actually vanish. So the isospin 0 guy vanishes at s equal to half, and the isospin 2 guy vanishes at s equal to 2. So this is the lowest order chiral perturbation theory result. So that's what you must mentally remember, that S0 is 0.5 and S2 is 2 to leading order in chiral perturbation theory. Now there is a more profound reason why these zeros should exist. This actually follows from partially conserved axial currents based on an argument that was developed by Adler. And so that's why these are called Adler zeros. And these Adler zeros, because they are based on symmetries, they should exist non-perturbatively, not just at the leading order. So that's why we can treat them as parameters to dial and ask in the space of Adler zeros what happens to the S matrix. Another thing that I should point out, although I'm saying all these things very quickly because I'm almost running out of time, is that the value of the Adler zero, 0.5 and the value 2 are unphysical. Unphysical in the sense that when you think in terms of the kinematics, S is supposed to be bigger than 4m square for physical scattering to happen. So because in the units where m is equal to 1, you require S value to be bigger than 4, these values 0.5 and 2 would correspond to unphysical region, which essentially means that you won't be able to probe these values experimentally. So what are the ingredients that you would like to put in to sort of get your first constraints so far as the S matrix bootstrap is concerned? So first of all, we want to demand that there are these Adler zeros somewhere. And then you have to use unitarity, but we will also use another input because we have to give some more inputs. I mean, otherwise we won't be able to get any constraints. The input that we are going to use, which is the only phenomenological information in this whole S matrix bootstrap game, is the value of the row resonance. So this is the phenomenological input that we will use. And then after you do all this hard work, what you want to compare, or what you want to sort of make sure that you have right, if you have the correct standard model S matrix, is you want to make sure that your scattering lengths are in agreement with experiments. So this is how you define scattering lengths. You take the partial wave amplitude and you expand, you do a threshold expansion, which essentially means that you do a Taylor expansion around s equal to 4m squared. And these scattering lengths are measurable experimentally, or you can do some lattice simulation and you can extract them. So one thing, again, a game that you can play using these relative entropy ideas is that this universal part of the relative entropy for various processes actually have definite signs. Now, depending on which process you're considering, if you're considering this process where you have identical pion scattering, it's positive. But you also have the other sign when you don't have identical pion scattering. So dq is definitely not positive always. So this is a counterexample to an intuition that you might have that maybe dq, this universal piece, which is a subleading piece of relative entropy, is always positive. So there's a more profound way of understanding these signs that is using dispersion relations, which I don't have time to get into, which essentially tells you that there are these d-wave scattering lengths, which corresponds to Lorentz spin 2 scattering lengths, which basically have a definitive sign. And that follows from dispersion relation arguments. So these signs can be motivated by these dispersion relation type arguments. But anyhow, after doing a lot of hard work, you get these exclusion regions. Now you can ask me how you get exclusion regions later on, so I won't go through this. But this white thing is what Guerreri, Penedones, and Vieira originally found. So this is where the Weinberg's version of Adler zero sits. It's in the exclusion region. So the leading order chiral perturbation theory Adler zeros are actually ruled out. And that's not surprising because the leading order chiral perturbation theory does not have any information about resonances. And to generate this plot, we have incorporated the row resonance. So the fact that the leading order chiral perturbation theory values are ruled out is not surprising at all. Now you can do more things. You can put in more constraints. You can actually put in some more experimental constraints and get a smaller region and so on. And then you can ask that where here does the standard model live? So basically the answer is that it'll live at some corner of the plot, like what I was telling you. So we can do a different version of the Bootstrap. So not the version that these folks have done, but basically motivated by the signs of these DQ relative entropy inequalities or the signs that come from dispersion relation arguments. So this is basically what we can use as inputs for our Bootstrap. So we will use the signs that are motivated. These two lines are signs that are motivated from this DQ argument. Of course, we are going to use the rho meson resonance position. So this is the phenomenological input. These signs are sort of not really phenomenological, but sort of appealing to some other arguments like dispersion relations, or if you believe in the fact that these DQs should have definitive signs and unitarity. And then you go ahead and run your semi-definite programming. And then once you get the space of S matrices, you can ask, where in the space of S matrices do we see things that are close to experiments? So just to benchmark a few things. So I will just take 5 more minutes if that is okay. And I'll quickly finish. So I told you that there are some values that are known, which are called chiral perturbation theory values. So this black is the tree level, the Weinberg version of the chiral perturbation theory values. This orange is the 1 loop, and the red is the 2 loop, and that is the state of the art for chiral perturbation theory. Nobody has done beyond 2 loops. So on the space of Adler zeros, this is where things lie. This straight line is the line of the Lovelace-Shapiro model S matrices. And the Lovelace-Shapiro model S matrices are non-unitary. Otherwise, of course, we would have declared victory and would have said that, oh, string theory describes nature, but that is unfortunately not true. So I can tell you a little bit more about the Lovelace-Shapiro model in case you're interested, but let me just skip this. So after you put in the constraints of unitarity and the special signs of the S and D wave scattering lengths, you get this river. So that's what we were telling you, that's what I told you in the beginning, that you'll get a river of allowed S matrices.
Sorry, a quick question. So when you
Yes.
say unitarity here, you mean positivity of relative entropy, or are you using monotonicity as well?
No, I'm not using monotonicity. So this
just
is
positivity as you
yes.
vary thetas. I see.
Yes. Positivity in the sense of DQ. So it's so as I said that depending on which process you're looking at, DQ is not always positive either. So DQ could be positive for these processes, but for another process it's known to be negative. So basically, so this is something that you can actually calculate in chiral perturbation theory. And I told you that there are dispersion relation arguments which govern these signs, but you could have thrown away the dispersion relation arguments and you could have said that no, DQ is fundamental and we will respect these signs.
But sorry, but I thought there was no first, like information theoretic argument for that.
Yeah,
the
no,
sign
that's right.
of DQ should be fixed. So are you using the yeah? Sorry, go ahead.
Yeah. So this one, the fact that DQ. So there are two ways of thinking about it. So the fact that all these signs should be respected you can prove them using dispersion relations. So dispersion relations are basically what follow from making some assumptions of the high energy behavior of the scattering amplitude.
Sure.
Which will end up affecting the low energy physics as well. So all that I'm saying is that we observe that DQ, so far as chiral perturbation theory is concerned, have these signs. You can use this relative entropy argument that we will continue demanding that even a non-perturbative S matrix will respect these signs, or you could say that no, we want the non-perturbative S matrices to respect dispersion relations, which essentially translates into the same signs.
I see. Thank you so much.
Yeah. Okay. So you get this space of river S matrices, and the Lovelace-Shapiro model intersects at very interesting regions. And I told you that this region A is essentially where you get S matrices which are compatible with experiments. In fact, only near this, so you can see if you sort of zoom in, you could see some kind of a bend that is happening near region A. So in some sense, it's a kink. Of course, region D is also a very sharp kink. Region D corresponds to some interesting S matrix, which does not have anything, as far as we can say, to do with pion scattering. Region A, of course, does. And you have to work a little harder to extract spectrum from this, and you will find that the Recce behavior happens only near this kink.
I have a question.
Yes.
So when you say things are nearby, is it just in that one section, or is it more generally in this infinite dimensional space? Like, have you
yeah.
neighborhood in other directions?
So we have studied we can study S matrices all along the riverbank. So we have studied all these S matrices everywhere along the riverbank. And we have also done some studies about S matrices inside the river, but then that requires this extra condition that your total scattering cross-section is minimized.
Right.
Yeah. So when we say that it is nearby, the way that we are classifying nearby, there are two ways of doing that. One of them is, of course, do a brute force calculation, and then you calculate the scattering lengths of these S matrices and scattering lengths of, say, an S matrix somewhere near region B or somewhere very far off. The other way of doing it is that you take this S matrix and calculate relative entropy using hypothesis testing, and you compare it with chiral perturbation theory. So these regions, little regions in green that I've shown you near region A and region C, are what are close to the chiral perturbation theory S matrix.
So, a question: if you don't put the, let's say, information theory constraints, what do you get? Can you see the difference?
Yes. So if you don't put the information theoretic constraints, what you get is the lake. The exclusion regions, that is the lake. Yeah. So if you just use,
no, you don't have it in the same plot. No, but that's
I had it. Yeah. So I have it in my earlier plot. I can show you. Okay. Maybe I can sketch it out. So the lake is actually has the outer boundary of the lake coincides with this AB region, and the lake actually goes around this AB, and then you get a small exclusion region, maybe around that size, if you can see my pointer.
Sorry, but it's not like one is a subset of the other. I thought you add more constraints, so you have a smaller region. I don't.
Yeah, I have a smaller region because the lake is an exclusion region, which essentially means that whatever I'm shading out is, whatever I'm shading out is excluded. Yes.
Okay, thank you. Yeah.
Yeah. Okay, so you get rigid behavior, you get more phenomenological stuff that you can extract by doing some more precise study and so on. And as I was telling you, that you can do this relative entropy calculation and study how close the theories are. Harsh, did I answer your question?
Yeah. So what I was asking is, can we compare more quantities, and will they still be close by, or
yes?
Is it something
so compare more quantities. You mean experimental quantities?
Experimental, or maybe
yes.
You can look at some maybe locations of zeros, other zeros.
Yes. Yeah. So when you compare experimental quantities, whatever is known, they are definitely close by.
I see.
So the resonances, the scattering lengths, they are definitely within the error bounds.
I see. Okay.
Yeah. Okay.
Thank you.
You can try more things. You can try more positivity. There are some generalized version of positivity which one can try, but it doesn't help you much. It doesn't reduce the space of allowed region much.
I see.
And so in the last 2 minutes, let me just tell you why, what is our thoughts, what is so special about the standard model? So this, one of the things is that what we studied, once you have an S matrix, you can of course extract the total scattering cross sections in the forward limit, because that entails taking the imaginary part, is basically the imaginary part of the partial wave coefficients weighted by 2L plus 1 and then summed overall partial waves. What you will find is that near the sort of standard model value, you have a sharp drop in the total scattering cross section. So this is, I'm dialing the Adler zero, and then I'm plotting along the river what is happening to the total scattering cross section. And I'm doing a little bit something more sophisticated. So I'm actually averaging because the sort of scattering cross sections are supposed to be thought of as sort of distribution valued. So I'm averaging over the scattering cross section. But whatever upper cutoff you put, it's the gross features don't change. So one of the expectations why you expect this drop in the scattering cross section was actually anticipated by Mandelstam. And Mandelstam in his beautiful physics reports actually writes in the following words that the narrow resonance approximation may be regarded as a kind of a weak coupling approximation, since if the resonance is narrow, all decay times are long and all scattering amplitudes are small. And he gives us kind of a dispersion relation based argument why you get a linear rigid trajectory if the widths are small. And of course, you can do a more sophisticated study. You can actually, because you can compare two very close nearby S matrices in the Adler zero planes, you can plot the derivative of with respect to the Adler zero value, treating it as a parameter, and you will find that the sharpest drop indeed happens close to the kink. Now, there's another very sort of intriguing thing that happens is that this entanglement power. So what I mean by entanglement power is essentially this quantity. So this is we are doing an averaging in the isospin space. So this d omega 1 is basically the Haar measure or the volume measure in SO3 or maybe O3 more specifically. And this defines for us what is entanglement power. So this is something that is known in the literature. These are the two sort of references. And you will find that, again, near the kink, there's a sharp drop in the entanglement power as well. And quite remarkably, even the Lovelace-Shapiro model seems to, near the kink, it sort of seems to drop to the Lovelace-Shapiro model value. And you can do a bunch of other stuff. But another thing that you can do, and this was sort of motivated by whatever studies we did over the last several months, is that, okay, you forget about all these dispersion relation based inequality signs that we have, that we inputted. So you can just put in the row resonance value, unitarity, and you could demand that the total scattering cross-section is minimized. And when you do that, you get this line, this black line. So this black line is what gives you the S matrices where for a fixed S naught value, it gives us the location of the S2 where the total scattering cross-section is minimized. So this is what the black line is. And black line also somehow surprisingly sort of passes very close to this region A. Also it passes very close to the region C. So it's quite interesting. So here I have not put in any SD wave inequalities, anything to do with relative entropy. So it's somehow is sort of crying out for a minimization principle. And of course, I told you that you can plot the entanglement power.
In the old days, people. Sorry, just one. Yes. In the old days, people would tend to think that you want to maximize the cross-section for strong interactions, like it's really strong. I know that that's opposite to chiral perturbation theory, but that's what people used to think.
Yeah. I see. Yeah, so if you maximize it, suppose somehow it seems to go against this narrow resonance approximation argument of Mandelstamm's.
Okay.
Yeah. But in fact, you can, maybe that's also an interesting question to ask, what is the line of maximum total scattering cross-section? Yeah, we have not looked into that, but one can also generate that and see how far it is. Anyhow, so I told you that along this line of minimum total scattering cross-section, you can calculate the entanglement power, and somehow it seems to have a local minima precisely near the neighborhood of the kink. So one thing that I must say is that generating these numerics is a hugely time-constraining business, and we had to struggle a lot. And I'm really hoping that Martin and others, maybe you can come up with cleverer ways of doing all this. And maybe the challenge should be that you should be able to do all this on a laptop and not use clusters. Anyhow, so let me conclude with a puzzle. So a puzzle which, unfortunately, because of the fact that I had to say so many things, I did not have enough time to emphasize, is that it appears that there are two interesting regions. One of them is this region that I've kept on harping, which is near this kink, this A, and another region which is sort of kind of far away. Sort of this region I've been focusing on because this is close to the chiral perturbation theory values, and this region I have sort of ignored. But if I just focus on experimental values, so experimental values essentially means that you're comparing with the S-wave scattering lengths. And there's also something that is known about the P-wave scattering length. So S and P-wave scattering lengths. And you also can compare with the spectrum of resonances. So this also appears to be reasonably good. I mean, it's not as good as A, but then it's reasonably good. It's nothing wrong. So I don't know as of now how to distinguish this region from region C. Yeah, so even this minima, this line of total cross-section minima also seems to be passing through somewhere close to region C. So one thing that is definitely different about region C from region A is that the effective range, there's a particular effective range corresponding to the isospin 2 effective range, which is an order of magnitude bigger in region C. So unfortunately, experimentally, we cannot measure effective ranges as yet, but that would be one way of saying whether the real true standard model respects chiral perturbation theory and whatever S matrices we have close to region A, or is there something really weird going on? There are a whole bunch of other questions, but I've gone way over time, so I will just flash this here. But the punchline is that one should look for a minimization principle. One should look for a principle which will isolate the standard model S matrix for us. But this is something that I emphasized. Oh, sorry. We will require a version 2 for numerics, and this is where I think finding a solution to the dual problem is very, very important because, for instance, we cannot really compare the widths. We cannot really compare the lifetimes as yet, because what we have found is that the widths have very slow convergence. So I don't know how to do that. But the hope is that once we have the machinery in place, one can do precision phenomenology with the standard model Bootstrap. So this is a version of the Indian jugaad. So let me just tell you what this slide actually means. So in India, we always dream big. We dream of having a Harley Davidson, but essentially what we have is some version like this, where you have a scooter that is made of literally boots. So we are just bootstrapping our way. But because of the fact that we sort of have sort of limited resources, maybe necessity here will be the mother of invention as well. And of course, here I should end with this slide where I have I owe special thanks to whoever has helped us out. So initially we started off with just using a 32-core workstation, but that was, we required substantially much more power to generate these S matrices. And that's where ICTS Bangalore, with the help of my collaborator, Rajesh Gopakumar, and the computing folks there, they were very nice to provide us cluster access. And we managed to do some numerical experiments during this COVID time. So I will thank you for listening, and then sorry for going way over time.
Thank you so much, Aninda, for the great talk. And are there any questions? I actually do have a question myself. So this splitting of the relative entropy in the limit of small delta x, the two pieces, you said there's a piece that was delta x squared over sigma, plus a piece that you call the universal part.
Yes.
And then you said the non-universal, I shouldn't call it non-universal, but the piece that's 1 over sigma.
Yes.
So hard sphere, you called it hard sphere. And you said this is much larger than the other one. Is that the intuition?
Yes.
How do we think about this splitting? Can you say a few more words about this?
Yeah, so here we are using the approximation that sigma is small so that you have a very sharp Gaussian peak, which is close to a delta function approximation. So the way that we are doing an approximation is that we are taking delta x to be small, but also sigma to be small. And we are sort of expanding in these two limits. And so, this piece in this limit always dominates over this second term, because this is delta x squared. This is also delta x squared, but then there is a small sigma that is sitting in the denominator. So in this sense, it is actually a straightforward calculation to show that just using the property of the probability density, this relative entropy, the way that we have set it up. There might be other ways of calculating relative entropy, but then the way that we have set it up using these support functions is always positive. So this fact that this is always positive gels in with that that sort of intuition.
I see. So, go ahead.
Yeah.
And then I'm just wondering whether there is. It seems from the point of view of information theory, what ideally one would like to do is to start with a formula like this and do some sort of use monotonicity, because that's sort of the mother of all inequalities in information.
Yes.
That's where all the non-triviality lies. Do you have any thoughts on how would you formulate this? It's just a vague question, but I'm just wondering whether you've thought about how to impose monotonicity. How would you approach it?
Yeah, I was thinking, and this is something that I've not had a chance to look at. I'll explain why in a bit. Is that something like strong subadditivity would probably be a better way of constraining these things because of the fact, first of all, I think it's a good question to sort of set up the strong subadditivity inequalities in using S matrices, because we have a plethora of experimental data that is coming from LHC. So I don't think anybody has probed the strong subadditivity constraints using particle physics data. I think it'll be a great exercise to do. And secondly, the way that we had thought about it, and this is what I remember, is that it seems like we needed to consider at least 5 particle scattering to do that calculation. So that's why we didn't go there. But
I see. So you're thinking of as like multipartite to get a multipartite system, you want more particles, right? To be able to trace. Yeah.
Yes.
Why do you say 5, not 4? Because for strong subjectivity, you need 3. 3 subsystems. You partial trace one of them to get something mixed, right? To get density matrices, and then you need A, B, and C, right?
Yeah.
So is there some sort of non-triviality that adds an extra step? I guess that's already pretty messy, but yeah.
Yeah. No, I have to reconstruct the argument. I just remember that this was the, maybe it was just wrong, but then this is the conclusion that we had reached, and that's why we never pursued it any further. But these kind of things, I think, must be pursued, because once you think in terms of the language of the matrix amplitude, in terms of these beautiful quantities that are there in particle physics, I mean, you can do so many things.
That's right. Thank you. So are there any other questions for Aninda?
No, I just want to say it's very nice that these information theoretic things give new constraints. Yeah, it's kind of surprising.
Yeah. I think this is, there are way cleverer things to do here. I mean, I think there are much better things to do, which I'm pretty sure one just needs to be more creative. The kind of things that Nima was asking also is probably will teach us something. I mean, how to impose the monotonicity of relative entropy? It's a great question. To be honest, I don't know how to do that. It will be important to figure that out. Yeah, because you want to trace out the subsystems. Yes.
So I have another question. So operationally, how do you impose DQ as positive, or do you impose those?
So yeah, operationally, what we did was we imposed the scattering lengths. So it's easier to impose scattering lengths. So because the fact that DQ is positive is in the threshold expansion. So this is something that I did not have time to go into too much details. But then when I said DQ has these definitive signs, it's in the threshold expansion. So you're expanding around s equal to 4m square.
Okay.
And that's where you find that these have these definitive signs. And it is basically translates into imposing the signs here that I've listed here.
Right.
Okay.
So are these also a direct consequence of the dispersion relations, or
so for
is there anything more?
Yeah, so the D waves, the D wave, which essentially means that the Lorentz spin is 2, that's a consequence of the dispersion relation. Okay. Okay. So there's one extra thing which we imposed in addition to this D wave, which was this condition. It looks almost like a D wave inequality, except that it does not follow from any dispersion relation, but it does follow from chiral perturbation theory. So if you take the chiral perturbation theory up to 2 loops, this condition is respected. So we imposed these guys. Now the S wave and the S, when you consider the S wave, there are no dispersion relation arguments. The dispersion relation arguments only start from D waves, because the dispersion relation requires you to consider what is technically called 2 subtractions, which essentially means that the amplitude has to fall off in a certain way. So it cannot grow faster than S square, so to speak, at infinity. So when you're writing down dispersion relations, you require to put in S cubed in the denominator so that the integrals converge. So S-wave scattering lengths, although they look very similar to the D-wave scattering lengths, these signs do not follow from any dispersion relation argument. However, chiral perturbation theory, if you look at the chiral perturbation and you work with chiral perturbation theory, does give you these exactly the same signs as what follow from here, in addition to an extra condition for the isospin 2 guy, like here.
I see.
Okay. So essentially what we are saying is that there is a version of the dispersion relation inequalities, which are what I'm circling here. And in addition, there are these extra things which follow from chiral perturbation theory. Okay.
So that's how these are from one loop calculations which you extrapolate.
No, so it's just 2 loops as well. I mean, the state of the art follows these signs.
So sorry, is it fair to say that you did not use any positivity property of relative entropy that you didn't have any other independent arguments for? Like there was no positivity of relative entropy. You coming from information theory, teaching us something
we
brand
didn't.
new.
Yeah.
I see. Thank you.
Yeah.
All right. Thank you so much, Aninda, for the wonderful talk. And thanks so much for giving us your time this late at night.
My pleasure. Thanks for all the questions. I enjoyed them.
Thank you, everyone who came. The talk is going to be posted on the YouTube channel as usual.